All right, Algebra 2, we're looking at section 7.1 and we're going on to part 2. And what we're talking about here is example 3. So we've got 2 more examples and I just wanted to have a little time to chat with you about it. So this first one is just like what we talked about before. They said find p of a squared if p of x is equal to this. You know what we're going to do. Literally, we're going to just rewrite everything where the variable of the function of this polynomial function is as a blank or as an open parentheses. And then to evaluate p of a squared, we're just going to plop a squareds all through this. And after we do that, it's pretty simple to see that this should be a squared. A squared to the third power, we multiply those powers, we get a to the 6th plus 4 a squared to the second power, which would be a to the 4th minus 5 a squared, and that's it. All right, that shouldn't be too bad for us. And we're going to do a similar thing here. It looks a little crazy, but we can handle it. Look what they asked us. They said, hey, find q of a plus 1 minus 2 times q of a if this is the case. Well, first thing we need to do is rewrite the thing with the blanks, but realize we're going to be using this q function twice, right? So I rewrote this twice in order for me to evaluate this guy, right? And to evaluate this guy. And then after I get those values, I'm going to substitute it back into this expression. So check it out. Here I'm going to evaluate q of a plus 1. So I'm going to go around to all my blanks and put a plus 1 in there. And here I need to evaluate q of a, right? So I plug a's in there. And so now that I've determined what q of a plus 1 is, and it eventually becomes this a squared plus 5a plus 8, you're wondering how? Well, after throwing that a plus 1 in there, I had to FOIL it. I had to take a plus 1 and multiply it by a plus 1. I got a squared plus 2a plus 1. Then I had to take 3 and use my distributive property and distribute it all through a plus 1. Now I'm going to join like terms together. I'm left with a squared by itself, 2a and 3a give me 5a. 1, 3, and 4 come together to give me 8. You see what I'm doing. And then now I plug my a value in and I join, well, there's really no like terms. I plug my a value in and boom, I have q of a. But what they asked me to evaluate was q of a plus 1, which I now know to be a squared plus 5a plus 8, that's this, minus 2 times q of a. Q of a being a squared plus 3a plus 4. You see how we did that? And now I'm going to simplify this term. Sorry for all the crazy arrows. Now I'm going to simplify this by rewriting the first part. This is a squared plus 5a plus 8. I'm going to distribute this negative 2 through the whole thing. Negative 2a squared minus 6a minus 8. And I'm going to join like terms together with some expert mathematics happening here. I feel really sluggish, that's why I'm saying that. I'm going to join that together. These guys come together and give me a minus a, and that's it. I get negative a squared minus a as my final answer. So look what we did. We rewrote the blank spaces to figure out what the value of q of a plus 1 was and q of a. Then when we found those two values, we literally just substituted into the expression in order to write down what the value is of this whole thing. Is that all right? I hope so. Let me know if you have any questions. I'll happily answer them. And let's look at our next example. All right, so here in example 4, we are being asked about end behavior. So here are the graphs of some polynomial functions. For each graph, we need to describe the end behavior, determine whether it represents an odd degree or an even degree polynomial function, and state the number of zeros, the number of real zeros that are represented here. Okay, couple things we need to do. Let's get started with the first one. Addressing this first part makes me feel like I need to write this down in this way. So the two things I'm considering is what's happening as x goes to infinity with f of x and what's happening as x goes to negative infinity with f of x. And so I wrote that down for each of them just so we can talk about it looking at the problem. So as x goes to infinity, as x gets larger and larger, what's happening to f of x? It's going down, man. It's getting negative. right? So it's going to keep going and it goes to negative infinity. So as x increases, y decreases. Similarly, the same thing happens as x decreases. As x decreases or goes to negative infinity, we see our function also going to negative infinity here. Make sense? All right. So let's take a look at this one. As x goes to positive infinity, as x is going out, we get a little dip, but we're thinking not what's happening here, but what's happening as x gets bigger and bigger and bigger, and we see from our arrow going up that the whole function, the value of f of x would go to infinity, and as x goes to negative infinity in this function, we see that it's going down, or f of x is going to negative infinity. With this one here, both sides are going up, so as x goes to positive infinity, so does f of x, and as x goes to negative infinity, so does f of x. It goes to positive infinity in both directions because it's going up, all right? So we answered the first part of the question for each of these, and then they asked us to determine whether it represents an odd degree or an even degree polynomial. And I didn't talk about this in this video, but I think I spoke to you about this earlier. When I have a linear, I have all this stuff here. When I have an expression, a polynomial function specifically, and I know its degree, I know a couple things about it. I do know what the thing's going to look like. And so I want you to just observe for me when I have an even degree polynomial. Let's ignore 1 for a minute. But when I have an even degree polynomial, you notice that both sides are going to end up in the same direction, right? And when I have an odd degree polynomial, as with 1, 3, and 5, notice that both arms end up in two different directions. I forgot I had erased this one. End up in two different directions, right? So either one is up, one is down, one is up, one is down, one is up, one is down. And so just from that information, that quick reveal there, we can determine whether we have an odd or an even degree polynomial. Here, since both arms are going in the same direction, we should know that this is an even degree polynomial. And because both arms are going in different directions in this one, this is an odd degree. I think you know what this is. It's even. Both arms are going in the same direction, all right? And then finally, state the number of zeros. If we remember, zeros are where the function crosses the x-axis. Where f of x crosses the x-axis is where we have a 0. This function has 2 zeros. This one over here only has 1. And finally, this one here has no zeros. All right. I hope that was helpful. Let me know if there's some things that I can clarify. I know it was a bit long-winded, but there's just a lot of little verbiage and a lot of stuff we need to know as we move through this section. Listen, take it easy, and I look forward to seeing you soon. Bye-bye.